see this document on the screen?
Yeah, we can.
Yeah, so in the last class, we were actually going through the calculations and we calculated bending stress, and then we also calculate the shear stress due to twisting moment. And we also calculate the bending stress due to the bending moment caused by this load P, which is basically acting in the vertically downward direction. And once we have calculated the magnitudes, the next question was that in which direction the stresses are acting, because when you actually look at the SolidWorks simulation, as we have seen, there are six components of stresses: sigma xx, sigma yy, sigma zz, tau xy, tau xz, and tau yz. So SolidWorks or any other simulation software is going to give you these many stress components for any type of simulation you do, especially for three-dimensional simulation. So if you are not very sure about which specific component to look at, you will not be able to make sense of the stress analysis. So that is what we were discussing last time, that these are the bending stress and shear stress that you all know how to calculate. But we also need to know whether this bending stress corresponds to sigma xx, sigma yy, sigma zz, or tau xy, tau xz, or tau yz. Unless we actually know which specific component we are working on, the simulation results will not make much sense. So that is the reason we stopped our discussion. So I asked you guys about the bending stress, and I said that, okay, if this is the coordinate system, x is along the axial direction, y is basically going upwards, z is going out of the plane of this, basically where this L-shaped bar is placed. So bending stress will be along x direction. So sigma bending is nothing but it will be equals to sigma xx. Does it make sense to everybody so far?
Yep.
And the point where we stopped, I mentioned that, okay, so if sigma bending is sigma xx, how about tau? So what will be the tau direction? So if we know the shear stresses due to twisting movement, so what will be that component of tau when it is basically going in this circular form, or basically in the circular cross section? So if you look at the cross section of this rod, it is basically circle. And if you look at the coordinate system, it will be y going upwards and z going this way. Is everybody with me on this choice of coordinate system I'm plotting?
Yes.
Is everybody with me? And is there anybody who doesn't agree with this coordinate system? Everybody agrees, right?
Yep. Yeah.
Yeah. And twisting moment is basically acting this way. So let's say this is the twisting moment T. So if I have to find the shear stresses due to twisting moment, I know at this point the shear stresses will point this direction. At this point, shear stress will point this direction. At this point, shear stress will point in this direction. And at this point, shear stress will point in this direction. Now, if you know the direction of the shear stresses, tau here, tau here, tau here, and tau here, which are nothing but given by this formula, I need to know what will be the subscript I should use, whether it should be xy, xz, and yz. Can somebody help me in finding out? Actually, let me ask somebody from our class list. Can I ask, if I randomly pick a student, can I ask Alan Roas?
Yes, Professor.
So can you help us to find what will be the subscript for tau acting at this point? So let's say there are 4 points, point A, B, C, and D. And if I'm talking about point D and shear stress due to, by the way, first of all, do you agree that the shear stress will point radially upwards due to applied twisting moment T in this direction?
Would that be tau y plus?
Sorry, come again.
Tau of y?
So I need two subscripts here. So which one, YZ or XY?
Y, y, z.
Okay. So just to make sure that you guys agree or you guys understand, let me go back to our very first description of stress components, and where we described we'll have a tube and it has got X, Y, and Z components, I mean axis. And if I have to draw the stresses, this corresponds to, can you help me, Alan? What will be this component? Stress acting on this face
It's XX.
is sigma xx, right? And then I have another stress component going this direction and this direction. Can somebody help me to find out what will be this component?
Tau xy.
Tau xy. And the reason being that the first subscript represents the normal direction. So for this face, what is the normal direction? It is the x direction. So that is the x. And the second subscript represents the direction along which the stress is pointed to. So it is y. Does it make sense to everybody?
Yes.
Yeah.
Yeah.
And if by the same analogy, what will be the stress component in this direction?
XZ.
See, perfect. You guys got that. Now coming back to this, our original cross section. So we have this cross section. Now in this, if my shear stresses are acting this way, so what should be my subscript? What is, if this is my cross section, what should be the first subscript corresponds to? First subscript corresponds to what?
X.
X, perfect, because its X is actually going perpendicular to the cross section. So always the first subscript represents the normal to the cross section. So on this cross section, the normal direction is basically in the X. And the second subscript represents the direction along which it is acting. So in which direction it is acting? Is it acting this stress
The Y.
Y? So this is tau xy. Do you see what I'm saying here, guys?
Yes.
Yeah. And what would be this subscript? What would be the subscript about for this tau?
XZ.
Mm.
XZ, perfect. You guys now got that. Now what will be this?
Tau XY.
XY. And what will be this?
Tau xz.
XZ, perfect. So now you see that it is the same tau given by this formula, but depending on its location and depending on the choice of coordinate systems, here it will be tau xy, but here it will be tau xz. So if you basically use in SolidWorks simulation, if you try to plot or if you try to see what tau xy looks like, so you will see tau xy will be maximum here and it will be somewhat zero here and it will be maximum here. So if you look at that representation, you will see why tau is going to zero at this point, because tau is not going to zero. It is tau xy that is going to zero at this point. At this point, this shear stress is now taking the form of tau xz now. So now if you plot tau xz, then it will be maximum at this point and this point. Does it make sense?
Yes, it does.
Yeah.
Everybody is with me. So that is basically what I pointed in the very last last minute of the last lecture. I was saying tau xz here, tau xy basically pointed downwards, tau xz again, and so on and so forth. So here just I wanted to recap of you understand about this specific subscripts we are using. Let me know if you have any questions so far, guys. Any questions, guys? Okay, if not, then what we are going to do today is going to do this specific example. This is the numerical example that's already there in your textbook, and example number is 3.9, which is in my edition, in my textbook, which is 10th edition. If you have a newer version, I'm not sure the example number, it may change, but it is the solved example. And what it is showing that you have got a transmission shaft and it has got two pulleys, and the pulleys are getting there is one smaller pulley and one bigger pulley. Smaller pulley is basically getting the drive from a motor or some other source of power using the belts which is going from the top and to the bottom. So if the top tension at the top side is 200-pound force and the tension at the bottom side is 1,000-pound force, so can somebody guess like what would be the direction of rotation of this specific motor and pulley would be?
It would be
Clockwise?
Z direction.
Sorry.
I mean, like clock. Yeah.
Take your time. I'm By that time I'm just drawing the specific schematic in my document and in my sheet of paper, and then we will go through the example. So we will actually extend the example as they are in the textbook. So we'll basically extend from what the textbook asks us to do, and we will see how we can apply the von Mises criteria and Tresca criteria and what is the factor of safety we can get. So we'll take this specific example, and I will give you a couple of minutes to determine what is the direction of rotation um, of this shaft would be, assuming that a smaller pulley is getting the drive from the motor. And if you are if you have already figured out the answer, you need to also explain why you are thinking that specific direction. What is the reason that you are thinking that this is the direction of rotation? Just give me a few more seconds. I'm almost done. Okay. So yeah, any specific thought? Don't know diameter, can't conclude which torque is bigger. Oh, yeah, okay, let me actually share the screen. So this is the smaller diameter pulley. Smaller diameter, and let's say the diameter here is as per the 8 inches, sorry, 4 inches. And this is the bigger pulley which has got the diameter 8 inches. So assuming now you know the diameter of the pulleys, so what is going to be the direction of the rotation, guys? This is your input. So which direction do you think it is rotating?
Clockwise.
And why do you think so?
The bigger force on the bottom is gonna counteract the top force.
I'm sorry, come again.
The force on the bottom is gonna make it turn clockwise. The 1,000 pounds.
Yeah. Okay, so let me actually draw another schematic here, which may make it easier for you to this is, let's say, pulley A. This is pulley B. I'm maybe changing the labels here. So we are talking about pulley A here, and it has got 200-pound force on the top, 1,000-pound force at the bottom, and this is your motor which is driving it, and this is the belt. So the tensions are basically pointing outwards whenever it is touching the surface. So now if that is the scenario, so this is pulley A, exactly this pulley A of 4-inch diameter. So it has got that 4 inches. Now forget about the inclination of this belt. Generally the belt are always inclined because they are wrapped around the pulley. So it will not leave tangentially as shown. This is a simplistic representation, but here it is more realistic representation where the motor is even smaller than this and motor is trying to drive this pulley. So if that is the case, the top surface or the top portion of the belt is having a tension of 200-pound force, the bottom is having 1,000-pound force. So what do you think, what will be the direction? It will be like clockwise or it will be anti-clockwise? So always you remember that when a pulley is rotating, it must have the difference in the tension on the two sides. If there is no difference in tension on the two sides, that means the pulley is not rotate. For pulley to rotate, there has to be, for rotation of pulleys, there must exist difference in tension on the both sides. Difference in tension or belt tension, as we say, difference in belt tension at two sides. So this is a tight side or called tight side tension, and this is called loose side of the belt on loose side tension. So loose side and tight side. So basically, if the belt is rotating clockwise, then only you have tight side on the bottom and loose side on the top. So basically the way to figure out which one will be tight and loose side, if the belt is rotating clockwise, you have to see this belt is trying to stretch, this pulley is trying to rotate clockwise and trying to stretch on the belt. So it is trying to climb on the surface of the belt. So that is basically going to be the tighter side. And here the belt is basically leaving the surface of the pulley. So here you don't have as much tension as you must have here. So basically the pulley is rotating clockwise direction. Does it make sense? So this pulley is rotating clockwise. Is everybody getting what I'm trying to say here?
Yes.
Yeah.
Any questions, guys? So this is basically rotating now. You know that this is rotating clockwise. Now the shaft is rotating clockwise. So these are basically assume that these are the bearing supports. And this is another pulley which is driving the load. So there must be a load that is driving this or taking the power output from this specific pulley. So from the power goes from motor to the pulley number A, and from pulley A it goes through this shaft, and through this pulley outwards towards the load. So the power transmission goes like this. So this is your input power coming from the motor. It goes through the pulley, through the shaft, and then through this pulley onwards to output. Okay, and the amount of torque that is being transmitted is given by the difference in the tension on the two sides times the radius. So that is force times radius, but it is just not the force, it is a difference in the force from the tighter side and loose side and times the radius. So torque input is given by 1,000-pound force minus 200-pound force times 2 inches. So it is basically 1,600 pound-force inch. And P output would be, again, the same formula where you have the difference in the tension of the loose side and the tight side.
Is it 4 inches or 2 inches?
So it is the radius, so force times radius. So
Is it 4 inches in diameter or 2?
4 inches in diameter.
Okay, thanks.
Yeah. So torque output would be in this case 500 pound force minus 100 pound force times the radius. The radius, you know, this is basically 4 inches. So 4 inches, and this is going to be 1600 pound force inch. So it basically means the torque has to be balanced. So this is the input torque, and the output torque would be basically balancing it in the other direction. So the output torque is basically going to be in the other direction. And that is how the torque is getting balanced. But the shaft is rotating in the clockwise direction. Does it make sense?
Professor, I have a question.
Yeah.
Your arrow on the top right pulley system, you have it going, no, the very right one
This one?
on the right top,
Which one?
the one top right, that one.
Yeah. Okay.
Why do you have that arrow spinning in a clockwise direction?
This one?
Yeah.
So basically I have loose side tension on the top and tight side tension on the bottom. So tighter side of the belt is at the bottom and loose side is at the top. So whenever you have the pulley that tries to climb on the surface of the belt, when you will have the stretching, maximum stretching happens in the belt. So that is why you have, on this is possible only when it is rotating clockwise. If it is rotating counterclockwise, then the belt would be leaving this surface. So this will be loose side and this should be tight side. But that is not what the values represent.
So does that mean the arrows on the figure on the left are wrong?
Why do you think it is wrong? So it is 200 pound force on the top, 1000 pound force on the bottom. Okay. I see what you are saying. Yes, you are right. This is not clockwise rotation. This is basically because of this arrow. It will basically try to climb on, stretch on this, and it will be counterclockwise. Thank you for correcting me. So here what we are having is basically two different views. So we are looking from this side and here we are looking from this side. So this is just that representation. So if you're looking from here, if the viewer is here, then it will be basically it will be acting like counterclockwise. But if you are looking from that side, it will be opposite direction. Does it make sense?
Yes.
Yes, thank you.
Yeah. So it is just the way that you are looking at. So if you're looking from this side, then it will basically looks like clockwise. But if you're looking from this side, it will look like counterclockwise. That's the difference we have here. Any questions, guys, so far? Are you guys following it, what we're trying to do?
Yes.
Yes.
Okay. So we have got torque input and torque output. And that basically means if I look at this shaft, transmission shaft alone, I have these are my supports, and it has got rotation is this way, but torque is going 1600 pound force inch, and here it will be 1600 pound force inch. And at the same time, what this shaft is basically experiencing So what the shaft is experiencing is a force given by the sum of these tensions, two tensions, and that will be 1200 pound force, and it will be 600 pound force at the bottom. And let me now have to use the coordinate systems here. So if this is your X, this is your Y, and this is your Z, then basically means you have got the load, the tension, the two tensions are basically trying to apply a load in the Z direction for 1200 pound force, which is sum of 1000 pound force and 200 pound force. And you have a total load of 600 pound force acting in the negative Y direction. Is everybody following what we are trying to do?
Yep.
Yes.
Yeah, everybody is with me so far?
Yeah, this is just you're just doing like not torque, right? Just forces.
Yeah, so I am representing the forces and the twisting moment. So this, because of the belt tension and the way where they are acting at the specific radius, so the difference in the tension times the radius will give me the torque, and similarly difference in tension times the radius give the torque at this end. So basically I see I have a torque basically balances out 600 pound force acting this way and 600 pound force acting this way. And then also we have a summation of the tensions that is trying to pull this shaft in the Z direction. And we have summation of this tension, 600 pound force is trying to pull this shaft in the Y direction. So I have got this representation of forces and twisting moments. Does it make sense, guys?
Yeah, it does.
Okay, so the next part is how to calculate the stresses in the shaft, and based on that, if you know what is the diameter or how to size the diameter of the shaft. So if I have to find a suitable diameter of the shaft which has to withstand these much loads and this is the twisting moment, what would be the sizing or what should be the size of the shaft, assuming that we have to use von Mises criteria or Tresca criteria, and assuming we have to have, so let's say we only assume Tresca. So we will use, let's say, both use Tresca criteria with factor of safety equals 1.5. Determine the diameter of the transmission shaft. Diameter of the transmission shaft for the static loading. So here we are only interested about static loading because we are not considered about what would happen when the shaft starts spinning. So we will actually explain, we will actually go through that topic in the next lecture, and we call that load is called as fatigue loading. So when the shaft is spinning, how the stresses change in the material. So we will actually discuss, I mean, there's a whole lot of chapter about that specific topic. We'll go through that. But let's say right now at this specific time, assuming that we are trying to analyze the stresses at one given instant of time. So at one given instant of time, assuming everything freezes, at this instant, what are the stresses coming in the material and how to find what would be the diameter, minimum diameter of the shaft with a specific choice of material. Let's say it has got a material of steel, and it has got a yield strength of 100 kilopounds per square inch, kpsi. So assuming these are the material, find the specific diameter. So can you guys help me to what should be the steps I should take?
Find the shear stress.
Find the shear stress due to what?
The 1200 and 600 pound force.
Okay, so before we actually start to find the stress, I mean, by the now everybody will be agreeing to the fact that if we have to find the determine the diameter of the transmission shaft for static loading using the Tresca criteria, we need to find the stresses, right? We need to find the maximum stresses. If you guys remember the Tresca's criteria, what does it say? Tresca criteria says that the maximum shear stress must be less than equals to your yield strength divided by 2 to avoid failure in the material, isn't it? Right? Right, guys?
Yes.
If you have the slides from the beach board, if you can also refer to that, or if you have a textbook, you can also refer to that. Basically, this is a Tresca criteria. I'm using Tresca criteria at this point of time because for von Mises criteria, there is a separate formula you need. We will go through that all as well. But first, since Tresca criteria is the simplest of all, we are going through that. So Tresca criteria says that the maximum shear stress in the material must be less than the half of the yield strength. The yield strength of the material we have assumed at this 100 kilopounds per square inch. Now, what we have to find out is what is the maximum shear stress this shaft is being subjected to. So if it has got an unknown diameter D, so let's say it has got unknown dia D, what are the stresses coming in the material? So to calculate the stresses, we have to first see what are the loads in the material. So can somebody tell me what this load is going to cause in the material? This 1200 pound force acting in the Z direction. Actually, let me ask someone from the class. Frankie Murillo. Not there. Okay. Jesse Wu. I'm just randomly picking someone from the list of attendees just to facilitate the conversation and discussion. So don't think that I'm just putting you at a spot or something.
Yeah.
So are you able to listen properly?
Yeah.
Yeah. So can you try to explain or try to just guess what is going to happen when you apply a 1200 pound force on this shaft, assuming the shaft is restrained at the bearing location. The bearing is not letting the shaft to move anywhere. It allows the shaft to spin, but it does not allow it to move in the Z direction or Y direction or X direction. So the bearing is basically preventing it to move anywhere. And I apply a load of 1200 pound force in the Z direction. What is going to happen?
Is the shaft going to bend towards the Z direction?
Perfect. It is going to bend in the Z direction. And which one will be the tension side and which will be the compression side?
The one on the left side will be tension, and then the top will be compression.
Perfect. Okay, that's great. And if everybody agrees with that, is there anybody who doesn't get that part? Is everybody following it so far?
Yes.
I couldn't hear it.
Sorry, come again.
I couldn't hear he said.
Oh, so what he said, he said that when you apply this 1200 pound force, it is going to bend in the Z direction. So it is going, if I make a planar representation, a 2D sketch of the beam in the YZ plane, sorry, not the YZ plane, but in the XZ plane. So this is X and this is Z. And here you are basically attaching a 1200 pound force. And similarly, if I basically draw the projection of this shaft in the XY plane, then I am basically getting a 600 pound force at location. This is location of the pulley of A, this is B, this is A, and this is B. Now, are you able to see what I'm saying here or what we are trying to discuss?
Oh, yeah. Thank you.
Yeah. So basically in the XZ plane, the shaft is going to deform like this. In the XY plane, the shaft is also going to deform like this. Okay. So if I look at the cross section, so I will have tension, stress due to bending in the Z direction. And similarly, if I look at the cross section due to the bending, I will have due to this 600 pound force, what is going to happen? This will be tension on this side, right? Right, guys?
Yes.
Yeah, positive and negative and positive and negative. So when you have bending moments appearing at two different planes, so this is appearing in the XZ plane. So in the XZ plane, you have the bending moment and the bending moment is acting along the y-axis. I mean, it is in the XZ plane. And this load is in the vertical y direction and it is causing the bending in the XY plane. So this is bending in XZ plane. And this is bending in XY plane. Is everybody following it? What we are doing here?
Yes.
Yes.
Is there anybody who is not following it? So if you guys are following, to calculate the stresses that are going to come at different locations due to bending moment caused by this load, what I need to do? I need to draw the bending moment diagram. And you guys agree that the bending moment diagram would look like this. This is point A, this is point B. I need to find the reactions. Okay, I didn't specify the distances. So distances is, I believe in the slide. Can somebody tell me what the distances are for each section?
It was all 10 inches.
All 10
Yeah,
inches.
10 inches.
Okay. So what will be the reactions at the supports? What will be the reaction due to 1200 pound force at this support and this support? If all are 10 inches, so this is 10 inches and this is 20 inches. So you know how to find the reactions. So if you find the reactions, it will be basically in the 1/3 split. So it will be 400 pound force, sorry, 800 pound force here. And it will be 400 here. So it will be 400 here and 800 here. Everybody is following what I'm trying to do?
Yeah.
Yes.
Yeah.
So the bending moment diagram for the XZ plane, would be 8,000 pound force here, and it will be 800 times 4, it will be 4,000 pound force inch here. Is there anybody who is not following why I got 800 and 400? I will explain it. If
I don't understand.
you don't understand that, okay. So what we are doing here is we are just saying we are finding the reactions. So how to find the reactions at any point due to the simply supported case, and this is we are assuming simply supported. So we have got 1200 pound force, and this is your 10 inches, and this is your 20 inches. So I take a moment about this point. So let's say this is C and this is D. So if I take this is D. If I take a moment about this point, can you help me to write the moment expression? Who was asking this question, by the way?
I was. Lance,
Can you spell your, can you say your name, because I cannot see who is speaking. Just
yes, it's Lance Collins.
Lance Collins. So can you help me to find the movement about point D?
What? It would go 20 times 1,000.
Moment, just a minute, about point D. Can you tell me what will be it equals to?
20 times 1,200.
Okay, and it will be positive or negative?
Negative.
Okay, let's say it's negative. Then
And then you have 30 times R1.
Sorry, 30.
So 30 times R1.
Perfect. And that should be equals to 0 for static equilibrium, right?
Yes.
And then it will be basically what? It will be R1 would be 800 pound force, yeah?
Yes.
And R1 plus R2 has to be 1200 pound force. So basically it will 400 here.
Okay.
Got it?
Yes. Thank you.
Great. So now once you have got the reactions, then the bending moment diagram just shows the R1 times this distance, which will be 8,000 pound force. And then here at this point where the pulley, this is location of pulley A, this is location of pulley B. So you have got 8,000 pound force in here and pound force inch. And for here, it will be 4,000 pound force inch. Little bending moment diagram. That's just that we have basically created, right? Is everybody following it or is somebody who is not following it? Everybody is good so far?
Yes.
Yes.
So if everybody is following it, can you quickly do it for this case, for XY plane? Because we have done it for XZ plane. Can you do it for movement about XY plane? Okay, guys. Can somebody help me? What will be the reactions and what will be the bending moment diagram looks like?
The reaction on the left should be 200 and the reaction on the right should be 400.
And it is the same 1/3 aspect ratio, so 600 times 200. Okay. And then the bending moment diagram will look like what? It will be
It would start at 0 and then go up to 2,000 pounds at A, and then it would increase to
at
4,000
B.
pounds.
So it will go to 2,000 pound force inch at point B, and then it will come down, right? No, it will be 4,000 here, and it will be 2,000 here. Yeah?
Yes.
Okay. So now what we have to do is we have 2 points where the pulleys, so these are the 2 locations where the stresses are going to be maximum, can be maximum. It can be at point A or it can be at point B. So for point A, I have got 2 types of bending moments. One is 8,000 pound force inch in the XZ plane. So, and you have on the XY plane, you have got 2,000 pound force inch. So what you have to do is, you have to basically find the resultant of the bending moment. So let me actually help you to see how we find, if we have a bending moments appearing in 2 different planes, how we can combine them together. So for doing that, what we have to look at is the specific cross section. And we have got our y-axis in here and we have got our z-axis here. So first we focus on the XZ plane. So in the XZ plane, what is happening that you are basically applying 8,000 pound force inch at location A. So we are basically drawing this cross section at location A. Okay. Because of this applied load, what is how the deformation is happening here? Do you see the deformation is happening like this? Everybody agrees with me? The curvature will be like this.
Yes.
Right? So what is in effect is happening? There is this, right? It's trying to bend like this.
Okay.
And the direction of that would be from the right hand thumb rule, and it is basically for this. Let me know if it makes sense. This is not in Y. About in the Y direction, the right hand thumb rule will will give the direction of the bending moment in the XZ plane. Let me know if it makes sense or not. And if you understand this, the rest of the discussion would be easier. But if you do not understand that, let's focus on this specific concept.
Professor, I don't understand it.
Great. So let's try to explain. Let me try to explain it again. So when you are applying a bending, when applying a load like this, in essence, what is happening that somebody is trying to rotate it like this, right?
Yes.
So what is the direction? If I have to basically represent the direction of the bending moment, that bending moment vector, if I say, then it is basically going to be pointed towards the out of plane of the paper,
Yes.
right?
Yes.
So that's what we are basically saying, that what will be the direction of the movement vector when it is deformed like this. So it will be pointing in the y direction.
Yes, I understand that part.
Are you getting what I'm trying to say?
Yes, I am.
So the right hand thumb rule basically says that thumb is pointing in the y direction. So that is what this bending moment is saying. This is what the bending moment in the XZ plane represents. And this is basically equals to your 8,000 pound force inch. Are you guys following it, or you're not following it at all?
Yeah, I'm following.
Yes.
Anybody who is not following it or who is having difficulty in understanding it?
That was me. I don't know why it's in the XY plane now.
Sorry, which one?
The one you just said, you said, okay, so it bends in on the Y direction.
No, it doesn't bend in the y direction. It bends in the XZ plane, but the right hand thumb rule of the bending moment would be pointing in the y direction. That's what I'm saying.
Yes, okay.
That is just the representation of bending moment. It basically says that the bending occurs in the XZ plane. Here it is deforming in the XZ plane. This is x-axis, this is z-axis. It is acting in the XZ plane. But the direction of the bending moment, the way that we represent, just like I have shown you on the last slide about the shear stresses. The shear due to torsion remains the same, formula remains the same, but you have to be careful about the subscript, whether it is tau xz or tau xy or tau yz, what is it? So similarly here, if I'm talking about the bending moment M, if I just talk about M, the M basically is this. It has got 8,000 pound force inch value here. It has got 4,000 pound force inch value here. It has got zero values at this end. But if I have to add a subscript to this M, then it will be normal to the direction normal to this plane, and the direction would be based on the right hand thumb rule for this for this movement.
Okay, I understand, but why is it on the right moment?
That's a convention we are using. So you can take a left as well, but then the convention has to be followed for the next part as well.
Okay, thank you.
Yeah, so that is a sign convention. We are just following that. If the bending moment is acting this way, this is called as positive bending moment, and it is acting in the positive y direction. This is your my. So this is your my. Now, if you guys agree with me, or let's say you somehow followed this, can you help me to find the bending moment direction for this?
It's in the Z.
It will be what? M?
Z.
Z.
Z. And the value, this is your MZ. And the value is basically at this point is given by 2,000 pound force inch. We are looking at point A. We are looking at point A. This is bending moment representation at point A. Are you getting what I'm trying to say here, guys?
Yeah.
Yes.
Yeah. And once you have got this bending moment as a vectors, then you can find the resultant of the bending moment, and that will be basically resultant of 8,000 and 2,000. You can find the resultant. Can somebody find the resultant of the vector? It will be pointing somewhere over here. So basically this is M resultant, and M resultant would be square root of my square plus mz square. So it is square root of 8,000 square plus 2,000 square. It will be some number, right?
That's correct.
So let me see if somebody has got the value 8246. Okay. So assuming this is 8246 pound force inch, this is what the value of resultant bending moment is. And the stresses, the maximum stresses would occur on a plane which is perpendicular to this resultant bending moment. So if the resultant bending moment is in this direction, you can find a direction as well. You can find at what angle this direction is lying, because that will be tangent theta to 12,000 divided by 8,000. So you can find this angle phi on which the resultant vector is lying. And the maximum stresses would occur in a plane which is perpendicular to this resultant bending moment. So the maximum bending moment would be bending stresses would be happening at these two locations, the sigma bending maximum and sigma bending maximum here. Are you guys getting this part?
Could you explain how you determined the dashed line? How you got that
This one?
direction? Yes.
This one. So if I know the resultant, which is you have found the magnitude, you can also find out the angle, right? Because you know that of that phi would be 2000 divided by 8000 tan inverse, right?
Yes.
And once you can find that, then you basically know the direction properly, and you can make a dash line which will be just like here. It will be just this angle phi.
Oh, okay. Thank you.
Yeah. So this is wherever this line intersects this cross section. This is the point where the maximum bending stresses would be occurring. Now it will be. I mean, which one, whether it will be tension or compression, you basically can determine that it will be tension on this side and compression on the other side. So it will be tension, mostly tension here. So this will be positive and this will be negative. But the maximum bending stresses would be occurring in a plane which is perpendicular to the resultant bending. Let me know if you guys are understanding it.
What did you write? Is that plus? What's the
This one?
subscript? Yeah.
This one?
Yes.
This is positive bending stresses here at this location. And
Okay.
negative bending stresses at this location.
What did you write? Is that a BE?
Plus VE positive and minus VE negative.
Thank you.
Yeah. Are you guys following it, or if there are any questions, guys?
Did you say it's positive because it's in tension?
Sorry, come again.
Did you say it's positive because it's in tension?
Yeah, this point will be in tension and this point will be in compression.
Okay.
And these are the points where the maximum bending would be occurring. So let me actually ask you guys. So if you look only, if assuming that this 600 pound force would not have been acting, this is basically making the things complicated. It is only this 1200 pound force is acting, which is this. So we actually know that this is the maximum bending moment, and this is the point at which the stresses would have been the maximum, which is basically, if you look at the YZ location would be this. This is the point at which the positive stress, this will be in tension, this will be in compression, right? This is what we have basically discussed a while ago. If everything else is not existing, if only this 1200 pound force is existing, then we know that this will be the positive and this will be negative. Maximum bending stress would be occurring at here, and this is the negative compression stress is acting over
Got
here.
it.
Yeah, everybody's so far.
Yes.
I will explain again if you are not following it, but you have to let me know. If you choose to not respond at all, then it becomes difficult for me to understand that whether you are following it or not. So that is my problem.
Professor.
Yeah.
I'm having a hard time seeing why it's in compression and tension in those specific areas.
Okay. So if you forget about everything else, if you just look at this, okay, and I draw the cross section of this, which will be circular, and the Y was pointing upwards, Z is pointing downward. Do you agree with this choice of cross section?
Yes, I do.
You agree. And if 1200 pound force is acting the Z direction, you agree that one part will be tension and another part will be in compression, right?
Yes.
So if bottom part is in tension, so in the cross section, what will be? It will be is this point or this point or this point or this point. What do you think? Which point is?
Which one would be what?
Which point will be the maximum? Will be under maximum tension. So let me say A1, A2, A3, and A4.
A1.
A1. So that's what I was saying. And which will be in compression?
A3.
That's what I was saying, right?
Yes.
A1 will be positive and A3 will be negative if only this is active.
Wait, Professor, but isn't your 1,200 pounds are going down?
Yeah, in the Z direction. Be very, very careful about the coordinate systems. If you're not careful about the coordinate system, it will be hard to follow what we are doing.
Okay, now I'm like, I don't know why. Just now I'm really confused. Okay, so this little circle that you have right here, it's ZY, right?
This one?
Yeah, that's viewing
from here.
The shaft from the front part of it.
From here.
Okay, so your Z direction is going down.
Going if I am looking from this side, I mean basically it is this shaft and I am basically looking from this view. This is my view. So I'm looking from this view.
Wouldn't the down direction be Y?
Oh, why it will be Y? Because if you look at this cross section, Y and Z, Y will be pointed up, Z will be pointed left. If you're looking in this is the viewer which is looking at.
That's why Z is pointing to a side, right? So if you look at it from the side.
Okay. Just give me a second. You agree with this specific isometric view?
Yeah.
Yeah. If I'm looking from this, I do see a circle.
Mm-hmm.
And my Y would be up and Z will be down, or sorry, in left.
Yeah.
You agree with this much?
Oh, wait. Yeah. Sorry. I don't know why I thought on the other, I thought on the main like drawing it was pointed down the 1200, but then now that I went back and looked at that you pointed it out. Okay, now I see why it's in the Z.
Okay.
That makes sense.
You are getting it?
Yeah, I just got confused with all the other stuff.
Yeah, there is a possibility of getting confused, and the reason you are going, everybody will get confused because of the directions. If you do not keep track of the directions, there is no way you can find what is MY, what is MZ, what is the result, and everything will be out of order. But if you follow the direction, the coordinate, the most important thing is coordinates. If you track the coordinate systems and you agree with this, everything will follow in place.
Professor, I have a question about the compression and tension.
Okay.
So since A is going down and I thought it would be compressing at the positive Z direction and tension.
Now you tell me whether it is basically compressing in the positive Z or negative Z.
Oh, I forgot the other side was making it bend the other way. My bad. I see my mistake.
Okay, no issues. I mean, it's possible. Take your time. I mean, this is not so trivial that it will strike immediately. It will take time, so it's okay. Let me know, guys, if there is anybody who is not following it. I will try to explain again. And that is the important part. If you understand this, the rest of the things are just applying formula and just calculation. So if you understand this, it's just thereafter you know what the stresses are. Now I can tell you the formula to find the bending move stresses. Then you find more circle, you do principal stresses, and everything else will follow in place. But do you follow this thing?
Yes.
Yeah, the same thing we have done for XY plane. And as I said, the resultant bending moment vector would be pointing in this direction because it is a resultant of My and Mz. Now M subscript Y is basically the bending moment for XZ plane. That is what you have to always remember. This bending moment acts in the Y direction, but it bends the beam in the XZ plane. It's positive Y direction, 8,000 pound force corresponding to point A. And similarly, MZ is basically bending in the XY plane, pointing in the Z direction. So in the Z direction, at point A, it has got 2000 pound force inch, that is the value. And the resultant of these two is basically pointed this direction, which is you have told me 8246. And I'm saying that the stresses, the maximum stresses due to this resultant bending moment would occur in a plane which is perpendicular to the resultant bending moment, and it will be here and here. Now one part will be tension, one part will be compression, and this part will be compression, and this part will be tension because of the direction of the vector. So do you guys follow this much?
Yes.
Anybody has any questions, you can address that. If not, then let me actually go and write the formula for the stresses. So what we have to do now, we have to find the sigma bending. Sigma bending, now you know it is just M divided basically D by 2 maximum, and it will be pi by 64 D4. Basically what it is I'm writing is My by I. So that is what it is, right? Y is basically D by 2, the maximum stress is occurring at D by 2. So if I go back here, the maximum stress it as is occurring at this point and this point from the center, which is at a distance R from the center, it is D by 2 from the center. So negative or positive maximum stresses are occurring at distance D by 2. So that is what it is showing. And I is pi D4 by 64 most of the cross section. And this is just simply 32 M by pi D cube. And this is M resultant. And D is your unknown diameter. At this point, we don't know what is the diameter of our shaft is. Everybody is with me so far?
Yes.
Let me actually redraw.
We're gonna go right here. So wait, I don't get it. Just go back the same way you're going. Yeah, they're eating. Like if you're going back to the COVID testing, like you'd want to go on that.
There are a lot of noise I'm basically hearing. Can you please question specifically if you have? This is how you calculate the stress at this point. Now this is due to bending moment. Is everybody following it, what we are doing so far?
Yeah.
Yeah.
The questions, guys. Okay, if not, then this is step 1. And we do not know the diameter. So our textbook tells us what's the diameter of the shaft is, but we don't know the shaft diameter. We have to find the shaft diameter based on the Tresca criteria we are going to use. And step number 2 is find the shear stress due to torsion. So how much is the twisting moment we are applying?
Is it the 82 or 8,246?
No, it is not 8,000. If I go back, if you look at, this is the torque that is being applied in this section. 1600 pound force inch. That is basically the difference in the torque input and torque output, difference in the tensions of the two sides times the radius. Remember? We have this additional twisting moment acting on the shaft. Yeah?
Yeah.
Yeah.
1600 pound force inch is the twisting moment. So if I apply that, 1600 16 times 1600 divided by pi d cube. Again, I don't know what the diameter is. So this is equation number 1 and equation number 2. And if you know what your sigma and bending and torsion is, and you have to find the shear stress, maximum shear stress, step number 3 is maximum shear stress. How to get maximum shear stress? So let me actually tell you the iterative method that as a designer you have to use. So there is, let me also tell you that for finding the maximum shear stress, there is a specific formula available that you can basically refer to in the notes or in the textbook. But we are not going to use any formula for that. For example, I forgot what formula is. So what I'm going to do, how to find the maximum shear stress? Can anybody make an attempt or guess how can you find the maximum shear stress? Any guesses?
You draw more circle?
Yeah, perfect. You draw more circle. So to draw more circle, I need to represent the stress element. So assuming the sigma bending is here, which I'm looking at this point. I'm basically drawing a stress element for this point, and I have got twisting moment, shear stress, tau due to torsion. Tau due to torsion is acting like this, and I have got only sigma bending. Then what I do a more circle. So I have got one point is 0 tau torsion, and another point is sigma bending torsion. Now I draw a more circle, but to draw a more circle, I need to know what the values are. Otherwise, I cannot draw anything in here, right? Are you guys following what I'm trying to say? If you remember the more circle concept, we basically need to mark the 2 points. I have 0 and tau and sigma bending and tau torsion. I don't know what this value is. Why I don't know? Because I have an unknown diameter at this point. Okay. Are you guys following what I'm trying to say?
Professor, I got a question.
Go ahead.
Where'd you get that 16 times 1600?
This formula.
Oh, okay.
It is basically coming from T times R by J, polar moment of inertia. Are you guys getting what I'm trying to say? I would appreciate any feedback, guys. If you choose not to respond, then I'm not able to understand it.
Yeah, we get it.
Yeah. Forward or I should stop at this point. Are you guys getting it?
Yeah, we're just watching. Well, I'm just watching Professor. I don't know about everybody else. Like,
yeah, I'm getting it.
Definitely, I'm gonna rewatch this whole lecture though. That's that's why I'm so quiet.
Okay. Now, what I was saying that I have to find a maximum shear stress. One way is you can find it using a formula, specific formula. So use an analytical formula, and that will give you shear stress as a function of diameter, unknown diameter d. And then use your Tresca criteria, step number 4. Use Tresca criteria, which says that your tau max has to be less than equals to, or n times tau max has to be less than equals to yield strength, or tau max is less than equals to yield strength divided by factor of safety. I know yield strength, factor of safety, yield strength is 100 kilopounds per square inch. Factor of safety, I gave you 1.5. So tau max has to be less than 100 divided by 1.5. So it basically means that function of diameter, whatever you will get, will be, can be equated it to, should be less than equals to 100 by 1.5, and you can solve for the diameter, unknown diameter of the shaft. Solve for unknown diameter of the shaft. Yeah. Let me actually also Let me actually give you the formula. Just let me actually look at the textbook. I will give you the formula here. Okay, so the formula is, as I was looking at the textbook, it is sigma by 2 whole square plus tau square. So tau due to torsion and sigma due to bending. So sigma bending is coming from this function, which has the unknown diameter d cube. Tau torsion is given by this expression, and maximum shear stress is given by this formula. I was not remembering that formula, so I looked at the textbook, and textbook gives me this specific formula. Now, when you put these values in this formula, you will basically get something in as a function of diameter d. Everybody is agreeing with me so far?
Yeah.
Yeah. So if you, with that, if you get the maximum shear stress, then use Tresca criteria that we know that it has to be factor of safety times the maximum shear stress should be less than the yield strength. And by using this equation, now you can solve for the minimum diameter that the shaft should have by using this expression for unknown diameter of the shaft, right?
Okay.
So that is one approach. Another approach is that instead of reusing this formula, I use Mohr circle. And how to do Mohr circle? I create a Mohr circle, and the Mohr circle for this specific example would look like this. And I know that maximum value of this circle will give me the maximum shear stress. So I can quickly get the value of the maximum shear stress using Mohr circle. But to draw the Mohr circle, I need to know these numbers. I cannot retain it in diameters form. So what I will do, I will approximate diameter. So let's approximate D as, say, any number, say 0.1 inches. Say, or rather, yeah, let's say 0.1 inches. Say. So if you when you assume this number D is equals to 0.1 inches, right away you know what sigma bending will be for that 0.1 inches, right? Because when you plug D as 0.1 inches, you can find the number value for sigma bending. Similarly, when you plug D is equal to 0.1 inches, you get a value for tau torsion. And once you get these values, 0 and something number, which will be this point, 0 and tau torsion. Sorry, it will not be this number. Actually, the Mohr cycle will not look like this. Sorry for that. It will be something else. It will be 0, tau, and sigma bending and torsion. So it will be look like this. So this will not be the Mohr circle for this case. So this is not the Mohr circle for that case. So the Mohr circle will be basically followed like that. So it will be 0, tau torsion, and it will be sigma bending, tau torsion. And having these 2 points, why I know these 2 points? Because I approximate ds 0.1 inches. So when I approximate ds 0.1 inches, I know what my diameter is 0.1 inches, and I know what the value of tau torsion, shear stress due to torsion is. And I know what is the normal stress due to bending is. So I know these numbers, I can draw a Mohr circle, and from there I can find what my tau max is. Let me know if you guys are following it or not.
So the center of the Mohr circle is where it crosses the x-axis?
Yes.
Okay.
So you just kind of predict it, right, Professor? Like obviously I don't know.
Yes. Yes, we are predicting directly. And the reason we are saying that, that's how all the design calculations are done. Design calculations are not done using this formula, because most of the times the formula are not known. So what we have to do as a designer is we have to approximate a specific diameter. So assume the diameter is 0.1 inch. That's my assumption. Now, based on that assumption, I found the stresses, create a Mohr circle, find the maximum shear stress, and let's say this is the number I'm getting. So I'm not going to say and see whether my maximum shear stress is satisfying this criteria or not. If it is not satisfying the criteria, then I straight away know I have to increase my diameter. And that is the iteration we have to keep on continuing. Is it making sense?
Yes.
Yes.
So I assume with the 0.1 inches, I do all the calculations, and let's say I found tau max as 105 kpsi. So is it satisfying this condition that tau max has to be less than equals to sy by n, 100 divided by 1.5? Is it satisfying this condition to avoid failure? Straight away no, right? This is value is much higher than this value. So that means my diameter, that's my assumed diameter, is very small. That means I need to increase the material of the shaft such that my shear stresses is reduced and I have to be less than this number. So then the next iteration would be, you assume D is not 0.1 inches. Let's say you make it 5 times or 10 times of this. So when you make it 10 times, so our next iteration, second iteration of your calculation, say D is 10 times of this original first iteration, and then you actually do all this calculation and you found tau some value, and you see whether it is less than or bigger than that. So if you find that it is much less than this, that means I need not to go for 1 inch diameter, but I can go even smaller. So that is what we do, the iterations. The calculations are happening in iterations to see when you satisfy the criteria for failure. Yeah, does it make sense?
Professor, how did you find the shear max 105? I know you would write it down and then just measure it to the top.
So what will be this shear stress max? It will be thus the radius, right?
Yes.
So if you plot these 2 points, and you can find these 2 points if you assume a specific diameters value. If you assume this, plot these 2 points, you can then measure diameter or the radius, and that will be your maximum shear stress, isn't it?
Yes.
So that is how I actually, and I said say because I don't know what that number is going to give me to. I know what my T is, which is 600 pound force inch. I know my M resultant, which is 8246, but thereafter, since it was taking too long, so I just now left the calculations. I didn't ask you to do the calculation. You can do it yourself and say if D is 0.1 inches, what this number is, what these numbers are, and what would be my tau max is going to be. So if
Professor, I have a
go ahead.
Oh, sorry. I have a quick question. So when you're doing the Moore circle, then it would be to scale, correct?
Sorry, come again.
So when you construct a Moore circle, it would have to be to scale, correct? Like this, what you're drawing isn't to scale right now?
Yes. It has to be scaled correctly.
Okay, so would there be like an inherent error in like us hand doing our Moore circles?
It should not be, in the sense that you can straight away, if you plot these 2 points and by using any specific scale, you can find the middle point. Okay, so what you are saying, that if there is a construction error, that's what you are trying to say?
Yeah, like
so
if we're doing it by hand, sometimes it does
so
happen.
it will be what? It will be not more than 5% error. I mean, that is not what you actually should be bothered about at this point of time, because you are trying to find a diameter that satisfies this factor with a specific factor of safety. So maybe 5% error, 10% error. So whatever that error is, that should be okay. I mean,
okay.
To say that is a construction. If you are really using that graph paper which doesn't have a minute scales or minute resolution, then that is a construction error. That's okay.
Okay. All right. So thank you.
Yeah. Let me know, guys, if you are following it. I specifically took this numerical example just because instead of asking you to do it yourself, I thought to do it myself and to explain you each step, because we have the bending moment appearing in 2 different planes. And once we have bending moment appearing in two different planes, it becomes very difficult to understand how the stresses are appearing and how to find the resultant bending moment, what is the bending stress, and how to find the location of the maximum bending stresses. So once we have understood this much, thereafter everything else, as I mentioned you before, is just formula. So you just plug in the values in this specific expression, you get a bending stress. You plug the values in this expression, you get a shear stress. You can construct a Mohr circle, or you can use this specific formula to calculate diameter. I mean, this expression will be a function of unknown diameter, and you can use again another expression for Tresca criteria, and you can solve for the diameter. So everything else is just algebra over here. There's nothing physical here to understand. It is just if you follow the algebra, or if you understand what the expressions are coming from, what they mean, then you're just following the algebra. There is nothing else. You're doing the maths here. What we are doing in the very beginning is we are trying to understand how the stresses are appearing, how the system is bending, and how to find out how to find the resultant bending moment which is causing the bending stresses. So that is what I was trying to explain you in this specific lecture. Let me know if it makes sense to you guys.
I'm confused on how to find the diameter still.
Okay, which portion you didn't follow?
When you approximated to 0.1 inches.
Yeah.
Are we just going to do that? And then you said keep doing that.
Okay. Let me actually, I skip the points here, or skip the steps. Let's say if I take d is equals to 0.1 inches. Can you calculate what that value would be, sigma bending would be?
Yeah, 1 second.
Yeah, go ahead. And similarly, you find, I would ask other guys to please help as well, because that will help to calculate it faster. So calculate the shear stress due to torsion when d is 0.1 inches, and calculate the bending stress when d is 0.1 inches. M resultant is 8246 and T is here 1600. So please tell me what that value is going to
be. 8.39 times 10 to the 7.
Wow, that's very big number.
Maybe I did it wrong. I'm not sure.
I mean, you may be right. I just took 0.1 inches. So it may be, you can basically, that may be the cause of. How about you take 1 inches? So that way it may have a reasonable number, because this is very high stress. Obviously it is going to not satisfy the criteria. How about with 1 inches?
I'm working on it. I'm sorry, 1 second.
Can I ask other guys to help here, please, as well? I'm just trying to get these numbers to show what these numbers actually look like. As we say, 0.1 inches is very, very high. So that means 0.1 inches is not a good approximation. We have to go close to this, to something that the stresses should be something in the range of 100 kilopounds per square inch, because our shear stress, maximum shear stress is given, the material strength is 100 kilopounds per square inch. If we are getting something more than that, that means it's very, very high.
The bending stress is 83,993.1.
Okay, 83,000.
993.1.
Okay, PSI, pound square inch, right? And similarly, what is this value going to be?
1 second.
I got 8,148.7.
8,147.7.
Yeah, 48.7, but same difference. Okay.
48.7 PS. This is for shear stress, right?
Correct.
Okay, so you got these two values. So it is something like 84 kpsi around. This is around 84 kips, kilopounds per square inch, and this is around 8. Approximating, I'm just approximating here. We can do the appropriate numbers later. So you get 2 points, 0 and 8 for this coordinate, 0, 8, and 8 and 84 and 8 for this coordinate. So now you just know how to find the, there are two coordinates, 0, 8 and 84, 8, and you know what is the diameter of that. If you just find the length of this line and you take the half, you will get the radius. That will be your maximum shear stress, right? Isn't it? And it is coming out to be, if I'm not wrong, it's coming to 42, half of this, right?
Yes, probably.
Yeah. So you basically tau max is 42, and it has to be less than 100 divided by 1.5. If it is less than that, that means d is equals to 1 inch is a good choice. If it is much less, then you can increase it slightly or decrease it slightly and see whether you can reach to this number, 100 divided by 1.5. Actually 100 divided by 2 times 1.5, because yield strength has to be 100 divided by 2. So it is SY by 2. It is 2N. Yeah, that's a correction. Okay. Is everybody with me? I don't know if we are exceeding the time, so I'm not sure if everybody is still there or following it or not. But did I answer your question? I mean, who is this? Who was asking this question?
That was Lance Collins and
Lance.
Yeah,
So do you see what I'm saying, or how we are trying to go here from here?
yeah.
So is your doubt now cleared how to find a diameter?
So you'll keep doing that until the formula is true that it's less than the safety factor.
Yes. Yes. This is what we call as iterative calculations. You have to go for iterations. So you approximate a specific value and keep on doing the iterations till you satisfy the criteria. And the criteria, it has to be less than 33.3 kips. And since we are getting 42, that means d is equals to 1 inches. It's still not a good choice. We have to increase it further.
Professor, you said that was for the bending moment at A. Does that matter if we use at A or B?
Yeah, that's a good question. So if you go for point B, then you have to find the resultant bending moment for point B. And if you see that, that is less than for point A. Because for point B, it will be resultant of 4,000 and 4,000, which will be 4,000 times root 2, which is less than what you are getting here. So this is the point at which you are getting the maximum bending moment, resultant bending moment.
Okay, so if you have a diameter that works with that one, it should be fine.
Yeah, so if the diameter works for this, then you are sure that it is going to work for point B. Right?
Yes, thank you.
Yeah, welcome. That's good questions. Any questions from you guys? If not, then I have basically shown you some steps. Now, since we are already exceeding the time, so I will not go further into the fatigue loading, but I would quickly wrap up with just one last concept. So I'm going to, I mean, it's just like what we are going to do in the next lecture, but imagine that this is your shaft cross section Y, and this is Z. And this is your positive stress, and this is your negative stress. Is everybody with me so far? Let's say that is how it is happening for this specific instant of time. That is what is happening. Is everybody getting what I'm trying to say?
Yes.
Yeah.
Yeah. So now the shaft is rotating. It is not stationary. So what will happen that if I just say that this is point A1 and this is point A2, that after half of revolution, what is going to happen that this point A1 would reach this location and A2 will reach this location. So A1 now will experience negative stresses and A2 will experience positive stresses. Earlier, half revolution ago, so at time t is equals to 0, time t is equals to half revolution, whatever time is. After half revolution, point A1 moves to this position and where it is experiencing negative stresses. And point A2, which was earlier experiencing negative, will go to this side, and that is with positive stresses. So you see the points keeps on experiencing positive, negative as the shaft keeps on spinning. And that is what we are going to learn next, which we call as cyclic loading. The loading goes like this, in a pattern like this. It goes like a positive, then negative, positive, negative, positive, negative, positive, negative, and that keeps on happening. These are cycles, and this is stress, positive stress, negative stress. So a material subjected to this type of stress, and we call this as fatigue loading, and that is what we are going to learn in the next lecture. Are you guys trying? I'm understanding what I'm saying here. This specific simple concept I was trying to explain.
Yeah.
Yeah, we get it.
Yeah.
Yeah. So this is what we are going to learn in the next lecture. But I hope you have understood this specific explanation on this specific concept that I mean this I just took it from the textbook, but just modified the version. I just modified it by saying that we are going to solve for the unknown diameter using the Tosca criteria. That's what we learned. So that is the only modification I did. Otherwise, everything else, the bending moment diagrams and everything else should be the same as the numerical examples on there. So it will be easy for you to follow if you read it from the textbook. Okay, guys, any questions before we wrap up today? Okay, if not, then I will see some of you guys on Wednesday lab session. Thank you, guys.
Thank you, Professor.
Thank you.
Thanks.
Thank you.
Thank you.
Thanks, guys.